Hey, it's working. All right, so we are talking about mountains. We've talked in the past about how mountains are formed usually at convergent boundaries, and that's not anything new. Now we're just giving some more detailed description into what causes mountains. So when we are forming mountains, we are going to be deforming rock. So this is when we're going to be changing the size and the shape of our rock. Again, it's usually going to occur along plate boundaries. And there are three ways that a rock can deform. So the rock can fold, it can fracture, or it can flow. So in order to change the shape or size of our rock, one way is that it can do so elastically. So we've heard the term elastic before, especially when we're thinking about like a rubber band, for example. And the idea is still the same. We're applying stress, and when that stress is removed, then the rock can return to its original shape. Obviously, that's going to take place over a long amount of time. And then, but if we surpass the elastic limit of that rock, so we apply just too much stress to our rock, then it will either start to flow if it is experiencing ductile deformation. And we've hopefully heard the word ductile before in reference to metals, but rocks can also experience ductile deformation. Or if that rock is brittle, then it will experience fracture instead of flow. So that just comes down to what type of rock we are talking about. So if the rock is either sedimentary or metamorphic, those tend to have weaker bonds between the atoms within the minerals, within the rock. And so we say that they would experience ductile flow versus our igneous rocks, which tend to have stronger bonds between those atoms, which make up the minerals, which make up the rock. And that ends up causing fracture, again, because they are more brittle, so they're not going to change shape willingly. If they experience too much stress, they're just going to break. So these are some pictures of some folds, because you may be thinking like, what, rock can fold? That's kind of strange. So that's what we see here in some folds of some mountains. And you see on the right there, those are called chevron folds. And I thought that was kind of interesting because there's a pattern called chevron, which is down here in the bottom left. So this is a chevron pattern, and obviously you can see that it's similar to these folds, as kind of zigzag, if you will. So with these different types of folds, again, folding is typically because of the stress that's being applied. So compressional forces just mean that it is like they're being pushed together, being compressed. So sometimes that leads to something called an anticline, and those are the pictures that you see here. So they are going to, again, be formed by compressional forces, and when it pushes, the center of the rock gets pushed upward. So we call that upfolding, or sometimes upwarping. And we can see from our little image over here, the center of the fold, that's where we're going to find our oldest layers. So we learned in biology about the law of superposition that says that the oldest layer is on the bottom, the youngest layer is on the top. So in this case, we've got this kind of teal colored one, that's our oldest layer, and our top layer with the yellow with the kind of zigzags through it, that's going to be our youngest layer. But because of that upfolding, forming this anticline, our oldest layer, our oldest rock could still be here in the center versus like over here, right, where these are pretty much in line. And over on the left, we don't see our oldest layer, but in the center we do. So again, our oldest rock layer will be in the center of an anticline. A syncline is just the opposite. So the idea is still the same in terms of how it's formed. The rock layers are going to be getting pushed together, but instead of upfolding, they do what we call downfolding. So we see a similar picture, except instead of it going upward, it's going downward. And the idea is still the same, that the youngest rock layers are in the center. The idea being, again, our youngest rock layer, before our oldest rock layers were in the center because of it being pushed upward. Now our youngest rock layer, so here this orange one, that would be on the top, and it is the youngest, but depending on how deep our syncline becomes due to those compressional forces on either side, hopefully we can see how like it could even extend like down here, right? And so our youngest layer might still be like quite a ways down just due to the syncline. So the idea, of course, is that our rock layers, although when they would originally form, maybe in these nice straight lines, these forces, compressional, like we've discussed for our anticlines and synclines, can make them either downfold, like we see in the syncline, or upfold, like we saw in the anticline. So they can be nice and symmetrical, like we've seen in our pictures already, or they can be asymmetrical. So basically, like they're a little bit of an angle. And if they're really at an angle, we say that they are overturned. So here are just some real-life pictures of some anticlines and synclines. You can kind of get an idea of scale because we've got this person standing here, for example. So now when we're talking about actual structures being formed, so not just layers of the rock that we see in the side of a mountain, but actual structures being formed due to upwarping, we call that a dome. So we can see a very large example of these two domes here in the background of this photo. So again, a dome is upward, and again, it could either be circular or, like it says, elongated, meaning more like an oval instead of as a circle. Basins are going to be the opposite of that. So again, we're talking about like a huge area, either circular or elongated, and this time instead of upwarping, we see downwarping, and again, that's a basin. So to give you an idea of like the size of a basin, like all of Michigan, we can see here is basically in this basin, and then we have an Illinois basin. We're pretty much in this Appalachian basin. So again, we're talking about huge areas of land. Since they have this downwarping, water can collect there. If the water just evaporates, then okay. But sometimes that water can sink into the ground. If enough water is there and it doesn't evaporate, then it can form lakes or marshes as well. So we've had anticlines and synclines, those are examples of folding. Our domes and basins are also examples of folding, just on like a larger scale, creating those structures. Okay, so now we're switching gears and we're talking about faults. So remember, with a fault, we don't have that nice folding anymore. We're talking about actually fracturing the crust, and we call those faults. So we have a few types of faults that we need to be aware of. The first category, I should say, these are called dip-slip faults. So a dip-slip fault is when, like it says, rock movement causes vertical displacement. Remember, vertical is up and down. So in this case, so I've got these two pieces of rock, Okay, I've got the one represented by the black triangle and this one represented by the red triangle, like on the side here. And we can see from the picture we've got this arrow pointing down, so it's showing that this red piece is kind of falling, right? It's moving downward while the black piece or this piece of rock is staying in the same location. So when they say vertical displacement, we're talking about, like, if we were standing here looking at this rock, we see that this piece of rock has moved up, right? It's moved vertically. So these two pieces, the black and the red, these are the footwall and the hanging wall. So the footwall is represented by this black triangle. The hanging wall is represented by the red triangle. So here's how we can remember that. If we were on the inside portion of our triangle, so here where I'm trying to draw a green line. So if we were here, we would be able to stand on that portion of the triangle. Okay, right? Our feet would be on the wall. On the red triangle, again, if we're looking at this portion, our hypotenuse, if we're thinking about math, we call this the hanging wall because this is where, and again, I'm not going to be able to stand here with my feet. I'm going to be hanging on with my hand. So in order to remember footwall and hanging wall, just think like, can I stand there or not? All right, footwall, hanging wall. Okay, so there are some different categories of dip-slip faults. This one is called a normal dip-slip fault, and in a normal dip-slip fault, what happens is the rock is actually moving apart. So we've already talked about compressional forces pushing things together. When they come apart like that, we call those tensional forces. And when that happens, it allows the hanging wall, right, the red triangle, that piece to move downward. We call that a normal fault. Okay, if they're moving apart and therefore the hanging wall is moving down, that's a normal fault. So I guess we're going to look at this picture first. Okay, so again, here's our real life example. We can see the division between our footwall in black versus our hanging wall shown in red. Now on this one, we see that the hanging wall is above, and we can really tell down here in the corner, right, that there's this missing space. So our red piece has moved up, our hanging wall has moved up on our footwall, so that will be called a reverse fault. So again, normal is if they're moving apart and therefore my hanging wall is moving down. But in this case, since my hanging wall is moving up, it is called a reverse fault. So now we just get to fill in those blanks about the things I was already describing. So they're both dip-slip faults. Again, we've got a hanging wall, we've got a footwall, there's vertical displacement. But in a normal fault, the hanging wall is moving down, as we can see here, right? Our hanging wall is below the footwall. In a reverse fault, our hanging wall is above the footwall. And if the angle at which that happens is like a low angle, I guess. So like it says here, less than 45 degrees. Like we see here, then that is called a thrust fault. So a thrust fault is a type of reverse fault. It's just kind of like, I don't know, shallower is kind of a way to think of it. And then, so these, again, all three of these, normal, reverse, and thrust, those are all types of dip-slip faults where we've got this vertical displacement of the hanging wall either moving up or maybe our footwall is moving up, again, vertical displacement. Our other type of fault is going to be a strike-slip fault, which we've usually called it a transform fault. So you can think of that as the same way as before. So we're just calling it a strike-slip fault now. Oh no, I don't know why this picture is missing. but it's okay. It was a picture of a mountain, and it had a thrust fault, and I can tell that because of, again, how reduced the angle is. So again, thrust faults can be small or large in scale. They occur due to compressional forces when our hanging wall is able to move up on the footwall. If they're moving apart, that's due to tensional forces, and that's called a normal fault. All right, so here we are with our strike slip faults. So again, instead of vertical displacement, remember vertical is up and down, now we're talking about horizontal displacement. So as we're either moving, this way or this way, we're talking about it being horizontal. So this land is still flat, unlike in a dip slip fault. In a strike slip fault, then the land is flat and we're talking about horizontal displacement or side-to-side displacement. So with mountain building, we often hear the term orogenesis, and that's just because the prefix oro can mean mountain, and genesis means beginning. So when we're talking about orogenesis, we're talking about the beginning of a mountain or creating a mountain belt. As we've discussed before, this often is going to occur at our convergent boundaries because our rocks are able to fold and fault and even go through metamorphosis with heat and pressure, chemically active fluids, like we learned in our second chapter. And that can cause our rock types to change as well. All right, so in those convergent boundaries, especially with continental convergent boundaries, we have discussed how neither piece of continental crust will subduct under the other, and we said that's because that continental crust just isn't dense enough. Okay, so it's going to be too buoyant, and because it is too buoyant or not dense enough, we say that it's going to demonstrate what we call isostasy, which basically just says that our continental crust won't subduct like oceanic crust does, and it's going to rest on top of the mantle, which happens to be more dense. And that's it. Thanks, guys.